Hi, Science 24s. Today we're going to be looking at Chapter 3, and this chapter is called Types of Chemical Reactions. Please make sure you have a piece of paper as we're going to be making a study sheet to go along with us, and I'm going to highlight key points that we should look and make sure that we have in our study sheets to help organize our thoughts. So this will be a little bit of a longer one, and it should take you about 2 to 3 class days as we make our study notes as we work through it because we have shorter classes. But this one will walk you through it. So please, if I'm going too fast, pause, see if you can copy notes, and then we can keep recording and going forward. We're looking at a chemical formula. We can think of this as a recipe and a recipe to make new ingredients. And these chemical reactions are going to be our cookbook, and we're going to see what makes what. And I like this picture, not just because I love making cooking analogies, and we've been talking about how chemicals are everywhere, like in cleaning supplies, but you can see all the different parts that go into making something else. And you can see if you want 2 chicken sandwiches, well, you'll need 2 pieces of chicken, 4 pieces of bread, some pickles, and what do you get? You get your 2 chicken sandwiches. I also like this analogy because we'll talk about this later, about the conservation of mass and how everything is accounted for on both the right and the left-hand side of that arrow, and you can see they're all in equal proportions. So right away, we want to start with some vocabulary. We have vocabulary here. We have reactants and we have products. So you can see here are the 2 words that we should have right at the top of our study sheet and our study guide. These 2 terms, reactants and products. I don't want to just go through and read it all as we're working through it because you can pause and copy it down, but I want to use my analogy of the reactants are all the ingredients you need to gather beforehand. The products is what you actually make with those ingredients. We're going to separate this with an arrow. And so when we see this arrow, that's what determines and that shows what we have produced. This one is a better way to visualize it and going through our chemistry taken right from the textbook and should be something right into your study sheet. It doesn't always happen with this where you have 2 reactants, 2 products. Sometimes it's 2 reactants, 1 product. Maybe it's 1 reactant, 2 products, okay? But this is our general formula where we have reactant 1 plus reactant 2 produces product 1 and product 2. We're going to have a few more definitions too. We have this definition of what is a word equation versus what is a chemical equation, and then how do we actually read these equations. And so for a word equation, this is where we're just putting in the words, but we're writing it like a chemical formula. And so you can see we have oxygen plus food or glucose, and that produces carbon dioxide and water and energy. In a chemical equation, you can see this is where I actually show the chemicals. So instead of writing out oxygen, I write out O2. And if you're not sure what the formula is, well, we're going to talk about how we break these down. But some of these are just going to be, you're going to get very familiar with. Same thing for food. Well, what is food? Well, it depends, but I specify glucose. The formula, the chemical formula, is C6H12O6. Same thing, carbon dioxide, CO2, water, H2O, and then we have energy being produced. This is our chemical equations versus our word equations, and we're going to practice reading both and becoming familiar with both. Here's a little test. Try to pause the video and see if you can write this as a word equation. So we see here, carbonic acid and calcium reacts to produce calcium carbonate. I've not given you any type of chemical equations or chemical formulas for each one, but I'm asking for a word equation. So all we would need to do is change our ands and reacts with plus signs and arrows. So what we would do is we have carbonic acid, there we are, plus calcium produces or reacts to produce calcium carbonate. Wonderful. If I was to give you the actual chemicals, you could probably put this as a chemical formula as well. But I would not expect you to memorize what carbonic acid is or what is calcium carbonate. We're not going to be there. You could do it if you're in Science 10 with our periodic tables or Science 20. But here we're working with our word equations and how to actually put them together, and we're just practicing reading through and knowing what they have for parts. We're understanding that this line separates out our reaction and that we know we have reactants over here and we have our products on the other side. This is a great example of we can have two things make one, and it's not always you have to have two things to make two things. Here we have two things and we put them together to make one thing. Here we're going to look at 4 types of reactions. Please make sure when we're taking our study sheet, we're going to have these 4 reactions, and this is great key terms that we need to put in. For our 4 types, as we're going through, feel free to pause, copy them down into your notes, and then listen to kind of how I explain and what are the details of them. What we see here, this is that example we had from the last slide, where we're trying to make one compound. And so my favorite way to visualize this is with the A plus B makes AB. But if you like, it's element 1 plus element 2 to create a compound. And so this is where we're taking two things and we're making one substance. A decomposition is the exact opposite. So when something is decomposing, that's breaking apart, and we can think of it that way. Decomposition is just like how bacteria decomposes different organic material. Well, decomposition is it takes this one thing, AB, and it breaks it back up into A and B, or the two different elements that it was made up of. A combustion formula. This one is key because we're going to see this all over the place. And this one we just kind of need to memorize. And this is what we'll kind of look at and what we saw off of our very first example. What the key is we have butane. However, this butane, it can really be any kind of fuel, anything that burns. And so for us, we take in glucose, we take in oxygen, and we produce carbon dioxide, water vapor, and we get energy out of it. So what we do as humans, we go through this formula. So I like this one. We can use butane as an example, but I also like to put in fuel because after that we have our fuel. It is the exact same details that we have in there for any combustion reaction. It's just whatever that fuel is right here, plus oxygen, always makes carbon dioxide, water vapor, and energy. We're going to talk about a little tweak later, but for now, a complete combustion reaction is exactly this formula all the time. Finally, our last one is neutralization. This is another formula where it's exactly the same, depending on what we have to start with. It's not just, oh, we have A and B like an acid base and make something else. It's not quite like that. Rather, we have an acid, we have a base, but it will always produce a salt and water. When I talk about salt, it's not like table salt. There is different types of salts, but this can be anything plus water. And that's what we're going to key off of is we have an acid could be something like HCl, where it's hydrochloric acid is the typical example. We have a base where it is NaOH. That OH is a dead giveaway. Whenever we see just an OH together like that, that's a giveaway for a base. And when they make and combine together, they neutralize each other and they make something called NaCl, which is just, for us, common table salt, and they make water, H2O. You should be able to go through and see where the parts kind of all mixed together and how they rearranged. This is our standard formula for neutralization. We have two things, they completely rearrange and they get something where we call them salt and water. This neutralization always follows the same basic formula. So with this one, please pause and practice these questions. This would be the first part of the notes where, okay, this is class 1, where we need to pause, work through these questions and see if you can identify what we've just gone through with different and new formulas and recipes of chemical equations. So pause here, work on these questions. They're great as examples to include in your study sheet on how you identify them. And when we get back to class, I can always review and see if we're on the right track. If you're ready, keep watching and we can go through the next set of notes. Now we're going to dive into a little bit more into the chemical formulas, and we're going to look at the chemical names of different things. And so we see here, we have our equation, we have our word equation where it's sulfur plus zinc to create zinc sulfide. So how do we look at the chemical formula? Well, we might be given a big table like this, where we have a common name for something, where you can see alcohol or antifreeze. We call some things baking soda. However, that's not their real name. That's not their chemical name. A chemical name really describes what the substance is, and each part of those words has a different important meaning. And so for us, when we're looking at this, let's look at ethanol. Well, ethanol, or when we look in other classes, eth means two-carbon chain. We see that here. The all part means there is an OH added onto it. So anytime you see an all, or this kind of ethanol, like an alcohol, they have an OH paired on with it. And then they just have hydrogens to fill the rest of the bonds. We're not getting into those details, but we have to know there's common names, chemical names, and then there's the chemical formulas. Some we've gone over. Look at sugar right at the bottom. We have sugar there. But sugar can be either called glucose or it could be called sucrose. And you can see how glucose, C6H12O6, a little bit different than sucrose, C12H22O11. A little bit different, but they're both types of sugar. Same thing here. I always talk about salts. Well, here's table salt, sodium chloride, but a salt substitute is potassium chloride. Or we might even see other types of salt. We've ever heard of MSG. There's other types of things that act like salts or kind of are flavor enhancers as well. Here I see Epsom salts, right? It's a magnesium sulfate. We just call them salts to kind of make it easier rather than talking, oh, pass the magnesium sulfate. One of the fun ones, if you ever watch baking shows, baking soda, we call this baking soda, but if you ever watch British baking shows, they will refer to it as sodium bicarbonate or just bicarbonate because they don't want to get it confused with baking powder because baking soda, baking powder, different, but important not to mix up. So we have all these common names. We don't need to memorize these. They're just some of the ones to kind of look interesting and work through. For ones that we need to put into a chemical formula, we should be able to be familiar with the periodic table when we look up sulfur, and we can look up zinc, But today we're going to be looking on how we actually balance these chemical formulas. So I talked about balancing, and at the very start of this video, I talked about how we have to have exact ingredients to make our sandwiches or to make our cookbook work. We need exact ratios of our recipe to make things work. We have to have 1 cup of something, let's say flour. We have to have 1 cup of milk. We need some salt. We need an egg. And in those proportions, we can make a cake. However, if all of a sudden we added 2 cups of flour and half a cup of milk, well, it won't turn out and it will be very, very dry. On the same note, if we added 2 cups of milk and 1 cup of flour, well, it might be just too soupy and it can actually thicken up and turn into anything. And so having these exact ratios is important. In chemistry, we need to go down to the exact molecule. And so a cup of flour might be different by a gram or two, but in chemistry, we need to go down and count atoms. And so when we're talking about things like this, we're talking about the law of conservation of mass. And I like this picture because you can count each of the colors of the atoms and see on each side they are identical. And so what we see on one side, we have 1 black carbon atom. On the other side, we have 1 black carbon atom. Here we have 1, 2, 3, 4 oxygens. And here we have 1, 2, 3, 4 oxygens. And then finally, we also have 1 here, 2, 3, 4 hydrogens. And same thing here. We have 1, 2, 3, 4 hydrogens as well. We have exactly the same amount of molecules. This is the law of conservation of mass. In any chemical reaction, we cannot create or destroy it. We just simply rearrange them. So if we start with 10 grams of reactants, we have to end with 10 grams of product. So what does this mean? We have this equation, one of the simplest ones, vinegar and baking soda. This is an acid-base reaction because we're going to be getting this sodium acetate, which is going to be our salt. We have our water, and then we do actually produce carbon dioxide gas. This is the one that makes baking soda and vinegar such bubbly fun and why it's such a staple in baking, because when we add baking soda to things, it reacts and it's a base and it reacts with anything acidic and it creates these nice bubbles and makes it nice and poofy and helps rise up things like cakes or breads. Now, what we need to do is, how do we count it all? And so simply, we can look here as one of the most complex examples, but we can go through step by step and see if something is balanced or not. So I just start with the vinegar and I say, okay, well, I'm going to count atom by atom rather than molecule. So I'm going to look here. I have 1 carbon, 2 carbon, 3 carbon on my reactant side. So I'm going to write 3 carbon. I can just put a C, or if I want to, I can go carbon. Now, on my other side, I'm going to draw a line here just to help keep it separate. I have 1, but I have a 2 there, so there's 2 here. And as I go along, I have 3 carbon. Perfect. So on my product side, I also have 3 carbon. Now let's grab another color. Let's try and count something else. Let's count my hydrogens. If you need to, try and pause and see if you can count and make sure we're on the same page. So over here, I have 3 hydrogens. So hydrogen 3, 4, 5. I have 5 hydrogen to count. Okay, as I move across, I have 3 here. I have 2 over here, so I went 3, 4, 5. Perfect. And I can go 5 hydrogen. And on the other side, I also have 5. Let's grab another color. Let's count oxygens. I have 1, 2, and I have 3 here. So 2 plus 3, 5. Over here, I have 1, 2, 3, 4, 5. Perfect. So I had 5 oxygen over here, and I had 5 oxygen on my product side again. Last one, we have Na, which is sodium. I have 1, well, that doesn't show up. 1 sodium. And on the other side, I have 1 sodium as well. Perfect. This one is all fully balanced. And so sometimes it does take just time to go through, count all the different pieces as we go through. We would call this a balanced reaction. Now, practice with these two. I'll erase this stuff. Practice with these two equations and see if they are balanced or not balanced. Hopefully you were able to figure out if the equations were balanced or if they were unbalanced. Now we're going to actually look and see how do we actually balance them. So when we look here, I want to keep a divide between them, and I just want to create a nice little table and count each parts of my reactants and my products. So what we see here is I have a chlorine, and I have 2 of them. Hydrogen, I have 2 of them. Over here, I want to do the same thing. I want to count them out, except I want to put chlorine at the top, just so when I compare them, it's much easier to look straight across and compare what I have and what I don't have. And so here I have 1 of each on the products. Now this doesn't work because you can see I don't have the same number. Just like our cooking recipe right from the start when we made our sandwiches, yes, we maybe take 2 pieces of bread and we made 1 sandwich. However, that sandwich still has 2 pieces of bread on it. It just made 1 sandwich and it made that 1 molecule. So we need to make sure everything is still accounted for. We might have taken those 2 pickles and put those 2 pickles on 1 sandwich, but in that sandwich there is still 2 pickles. So we need to balance that. And so what we can do, we can only change the number out front. With that number, I mean this big number right here. You see how I put a 2 in front? That is the only thing we can change in a chemical formula. So once it's made, we cannot change and add in small little numbers how we want. We can't just erase them and just say, oh, let's just ignore this, or let's just ignore this, because that doesn't work. These chemicals have been made. We can't just erase them or add them once it's been made or we've been told what's what. So the only thing we can do is say, oh, we have 2 of these molecules instead. And so what that does is it essentially says we have 2 HCl, meaning it times everything by 2. So we go 1 times 2, and we go 1 times 2 for the hydrogens. Now all of a sudden, when we go 1 times 2, we have 2 of them, and we have 2 of them. Now we are in a balanced formula. Let's try this with the second one as well. Pause and see if you can balance this one before me. So here I draw out my table and I want to count everything I have. So I have Fe, a capital letter, lowercase letter is always together, oxygen there. I have my Fe over here, and then I have my oxygen here. I count, I have 1, I have 1, perfect, I have 1 Fe. Oh, oxygen, I have 2. So remember, I cannot change the small numbers. Can't just erase it and say, hey, job's done. Can't do that. Only thing I can do is add numbers in front. So if I add a 2 in front of here, that's like I go 1 times by 2. 1 times by 2. Perfect. That means now I have 2 oxygen, but now I also have 2 iron. That's fine, because I can do the same thing here, add a 2 there, and that means I'm going times by 2 here. And now my iron has also gone to 2. And now I have 2 of everything through my whole equation. And so what I see here are my coefficients of 2 iron oxide makes 2 iron and 2 oxygen. The last little bit I want to talk about, in front of the oxygen, it isn't just a 0, there is technically a 1 there. However, we don't just put 1 because we write oxygen 2 there. We don't just have to say that there's 0 or 1. It's a given that there's always at least 1. If there's ever more than 1, you can put that number in. Great job. Now here's our last little checkpoint. Please work through these A, B, and C questions. Tell me if they are balanced. That's the important part. Can we identify how they are balanced? And then to push yourselves, because, well, it might be a test question or a quiz question, hint, hint, please try and see if you can balance the ones that are not balanced. So some will be balanced, but which ones are not balanced? How can you change it? And so remember, you can only change the big numbers out front, okay? We cannot change the small little numbers. We can only change those big numbers out front. Because remember, there's a 1 there. We can only change it if it needs to be a 2, 3, if it needs to be a 7. Those are the only numbers that we can actually change, okay? So practice and try to balance these questions. Perfect. Here is the list of key terms that we should have on our study sheet. We've gone through the word equations, we've gone through simple decomposition and simple composition. We talked about chemical names and chemical formulas, common names. The last one that we want to go over is those numbers that were out front are called coefficients. Okay, and so when we look at those big numbers, those coefficients are the only thing we can actually change. Aside from that, please make sure your study sheet is complete. Work through your Chapter 3 assignment and make sure to get above 50% so you can write your quiz coming up next week. Thank you and have a great day, guys.